What's up, guys? Welcome back to the channel. Today, we are going to be attempting some practice questions on paper chromatography. That means if you haven't seen the video on paper chromatography, you might want to check that out so you have an understanding of what the RF value is and how to calculate it. Because today, we're going to be attempting a number of questions based on this principle. Now, throughout this video, you feel free to pause and attempt some questions on your own before you press play and actually watch how it's calculated. Without wasting any much time, let's jump into question one. A mixture containing three sugars gave the following distances. So you have sugar X, Y, Z, and the distance moved in the chromatography paper, and the solvent front moved 9.6 cm. We're told to calculate the RF value for each sugar and arrange the sugars in increasing order of polarity, and then suggest which sugar is most strongly retained by the stationary phase. All right, so solution. First, we'll be using the formula RF equals to distance traveled by solutes all over the distance traveled by the solvent front. So for sugar X, that gives us 2.4 divided by 9.6 cm. For sugar Y, that would be 4.8 divided by 9.6 cm to give 0.5, and for sugar Z, that would be 7.2 divided by 9.6 cm to give 0.75. So next we are told to arrange the sugars in increasing order of polarity. Now recall that in paper chromatography, the less the distance moved by a solute, the more polar that solute is. So in the stationary phase is polar basically, while the mobile phase is generally less polar. So obviously the smaller the RF value, the more polar a substance is. So arranging that, we would have Z, since we are talking about increasing order of polarity, that means the shorter distance and smaller RF value would be the most polar solvent. So it's Z, Y, then X being the most polar. So this obviously translates to the C part of this question because we're going to be talking about retention. Retention is inversely proportional to the distance traveled. So because sugar X moved the shortest distance and has the lowest value, it has the strongest retention for the polar phase. So it is more strongly retained. It likes the paper more than any other sugar. So sugar X is more strongly retained. So moving on to question 2 now. The following RF values were obtained using N-butanol, acetic acid, and water in a ratio of 4 to 1 to 5. So we have amino acids that were run on the chromatography paper, and we have the following RF values. An unknown sample migrated 6.6 centimeter while the solvent front traveled 12 centimeter. We have to calculate the RF value of the unknown and identify the amino acid present. Now, if you recall from the paper chromatography video, one of the uses of paper chromatography is in the identification of an unknown solute, and this is a very good example of that. So let's go straight into it. So these are the RF values and the different amino acids. So to calculate the RF value of the unknown, we use the same formula: distance traveled by solutes divided by distance traveled by solvent front. And then we're given the distance traveled by the sample. This is for the unknown now. The distance traveled by the sample to be 6.6 centimeter and that of the solvent front to be 12 centimeter. So obviously the RF value will be 0.55. Okay, so that's the first part of the question. And the next part of the question is to identify the amino acid present and justify your answer. Now, if you look at this value of 0.55, let's go back to the table and see if it matches any of the RF values. You can see that it matches that of valine. So the unknown amino acid present is likely valine. This is because its RF value perfectly matches that of valine under the stated conditions. So obviously, when they migrate up, they would both have the exact same 6.6 centimeter. Now heading on to question 3. In an experiment, the same compound gave the following results. Distance moved by the solids as 5.2 cm. Distance moved by the solvent front as 8 cm. To calculate the RF value, and if a more polar solvent is used, predict whether the RF value will increase or decrease for a polar compound. Give a biochemical explanation. So the second question is a little more technical, but let's start off. So to calculate the RF value of the unknown, we use the usual formula, and given 5.2, that will be 5.2 divided by 8.0 cm to give 0.65. Now next we are to predict whether a more polar solvent, what would happen if a more polar solvent is used. So we must first understand the mechanism of paper chromatography, and it is based on the partitioning of solids between two phases, the stationary phase and the mobile phase. But this stationary phase in paper chromatography is highly polar. So a polar compound naturally has a strong affinity for this phase. That's why you see that a polar compound binds more tightly to the stationary phase. But when the polarity of the mobile phase is increased, we're not talking about the stationary phase now, the mobile phase is increased, the polar compound becomes more soluble in the solvent. If the solubility in the solvent increases, it means that no matter how much that polar solute likes polar the paper, it means that it now has an opportunity to move higher, because the compound now partitions favorably into the mobile phase, so it spends more time moving than sticking to the paper. This is because like dissolve like. So a more polar solvent would increase the solubility of that polar polar solute that was kept on the paper. And this increased time in the mobile phase will allow the solute to travel a greater distance relative to the solvent front, directly increasing the RF value. So therefore, a more polar solvent, if a more polar solvent is used, the RF value for the polar compound would increase. So question 4 now. A mixture of amino acids was separated using two-dimensional paper chromatography. So for the first solvent, the RF was 0.25. For the second solvent, it was 0.6. But first, we have to explain the significance of using two solvents in the first place, and B, if the solvent front in the second dimension traveled 10 centimeter, calculate the distance moved by the amino acid in that dimension. Okay, so it's a two-part question. First, we want to discuss the significance of using two solvents. Now, in two-dimensional chromatography, using two different solvents is significant for enhancing the resolution and separation of complex mixtures. I don't want to go over this so much, but you can get a lot more detail from the video on paper chromatography. I will also leave a link in the description. But basically, what happens is you run a sample in one solvent, usually an aqueous solvent. So you run a sample, and it would separate into its different components, and then you rotate the paper. You remove air dry, and then you rotate the paper 90 degrees and run the same chromatography paper in a different solvent to enhance separation. Now, what happens in the first dimension is that the mixture is separated into different amino acids. Some of these amino acids may overlap, but um, in the second dimension, that's after rotating 90 degrees, some of these amino acids that may have had the same exact weight are forced to migrate to a new direction, separating them further. So, because it is unlikely that two different molecules would have identical RF values in two different solvent systems, this method allows for the complete separation of components that were unresolved after the first run. So, anything that did not separate the first time will definitely separate the second time. That's basically the significance of this method. But all of this was explained in the first video, though. So for question 2, I'm also going to go back to this formula: distance traveled by solute divided by distance traveled by the solvent front. And we're being asked to calculate the distance moved by the amino acid rather than the RF value. So we are basically looking for the numerator. So we rearrange the formula so that the distance traveled by the solute is equal to the RF times the distance traveled by the solvent front. We have our RF to be zero point 0.6 in the second run, and then the distance traveled by the solvent to be 10.0 cm. So just multiply and we get 6 centimeters. So the distance traveled during the second run The distance traveled during the second run is 6 centimeters from where the sample spot was made to where the solute traveled to. So in the second dimension, the amino acid traveled exactly 6 centimeters from the origin created after the 90-degree rotation of the paper. For question 5, a student forgot to mark the solvent front immediately after removing the chromatogram. The solvent front was later estimated as 11 cm instead of the actual 12.5 cm. The solute distance was 6.0 cm. Calculate the incorrect RF value obtained by the student. B. Calculate the correct RF value, and C. State the percentage error. The first question should be, why did the student make such a mistake? But let's take it step by step. So the incorrect RF value would obviously be the solute distance divided by the incorrect solvent front. So using the usual formula, so that's 6 cm, the distance traveled by the solute divided by the incorrect distance traveled by the solvent. That gives us 0.545. So this is what the student got incorrectly. And then the correct ROF value, what the student was supposed to get, would have been 6 divided by 12.5 to give 0.48. And next we have to calculate the percentage error. So the percentage error will be the incorrect value minus the correct value, all divided by the correct value times 100%. So that's incorrect minus correct divided by correct times 100. That gives us 0.545 minus 0.48 divided by 0.48 times 100, giving us 13.64%. So it is by this percentage that this careless student was off in his calculation. So I've decided to add two bonus questions that I would have loved to get into, but it's easier to give you guys something to practice, to make sure you try your hands on these questions. And if you have any problems, feel free to let me know in the comment section. So that brings us to the end of this practice video. I hope you learned a thing or two about how to calculate the RF value and how to apply the RF formula in paper chromatography questions. Feel free to let me know if you have any questions in the comment section. As always, make sure you give this video a thumbs up, subscribe if you haven't already, and I will see you guys next week. Bye.